And you can see my screen, am I right? Okay. So now the thing now is this, okay? So we know that the design is going to be from point B, at point B. We're going to focus at point B. And what you see over here on the right hand side, this is the cross-sectional view. At point B. Okay, this is our cross-sectional view at point B. And one thing that you will learn in this course also is failure analysis. Okay, it's what we call failure analysis. Okay, so if we look at failure analysis, before I even go on in failure analysis, I will highlight two things now. Okay, before I go on, I'll highlight two things before we go into failure analysis. So what you see over here is the cross-sectional view. And there are two formulas that we're going to apply. Okay, there are two formulas to apply. So the first formula we're going to apply is stress in the x direction would be equal to mz over izz multiplied by y. Okay, and we have known that our mz, okay, our mz we have found is equal to what? Minus omega L squared over 24. Let me write this better. Minus omega L squared over 24. Okay. So if you look at how this equation will distribute the normal stress. Okay, so now I'm going to sketch the stress distribution. Okay, so over here we have our normal stress direction. Okay, and over here the vertical axis is going to be y. So again, this is just a sketch. So the normal stress distribution will look like this. Okay, so the normal stress distribution will look like, come on, Eugene, will look like this. Okay, so this is how the normal stress distribution will look like. Yeah, I'm just eyeballing this. Okay, so this is how the normal stress distribution will look like. Okay, I want to make sure that it looks symmetry. That's important. Yeah, it's better now. Okay. So this is how the normal stress distribution will look like, and we know at a certain distance. Okay, what I want you to highlight is this: at a certain distance of y, you have a value of minus mz over, or this is your negative stress max. Okay, and then at a certain distance where we have our negative y, okay, so one is positive y, one is negative y, we have our positive stress max. And exactly at the center over here, our normal stress is equal to 0. Okay, so at this line over here is also known as our centroid, and is also known as our neutral axis. Okay, based on, pardon me, I have to put a minus sign down here, based on this formula that we're using. Okay, if you sketch the graph out, it looks like this. Okay. Now we have also attained the shear stress. Okay, so shear stress, the equation is equal to Vy over Izz Qz over T. Okay, so now I'm going to sketch. Okay, now I'm going to sketch the shear stress distribution. Okay, I'm going to sketch this out. So again, this is our line. This is our shear stress. And then we have our Y. Okay, this is our Y. And I think I'm going to sketch a line over here to show me where are the limits of our structure. Okay, bear with me. So this is the limit of our structure, the green line. And another limit, the green line. So again, pardon me. Hey, where's my green line? My green line gone disappear. Okay, so this should come back a bit. Okay. So what we see over here, okay, I'm going to sketch how the shear force will be distributed. Okay, so what we see over here, again, this is a sketch. It will look like this. Then you go straight up. Don't worry if you don't know why yet. Okay, once I start teaching shear stress, you will understand why. Then you have this distribution, and you have over here, and you go down to 0. So over here, this is where your tau max is. Okay, this is where your shear is equal to 0. Okay. Again, over here, this line over here is known as our centroid. Okay. Now, what is the problem? Where, at which point in this cross section or in this structure, we are going to calculate our normal stress and our shearing stress. Okay. So if some of you say, why not we do point A? Or it's no good to call this point A because we have point A. So why not over here? This is our point I. Over here is our point J. Okay, right. So if you look at point I, if we were to view point I, right? If we were to view point I, if we were to just look at point I, right? At point I, we know that we are going, our normal stress is equal to minus stress max. And then our shear stress is equal to what? 0. We totally ignore the stresses induced due to the shear stress. Okay, so point I is not really a good point to choose. Okay, then we look at point J. So at point J, stress X is equal to 0. The shear stress is equal to tau max, right? Because over here, right, we have our tau max. Then this is where we come like, this is also no good, right? We totally throw out the shear stress, or we totally throw out the normal stress. We just focus on shear stress. So where is the right point to calculate this? Okay, so the right point to calculate this, if I'm going to zoom into this figure, is exactly over here, and this is called our point alpha. Now, what you realize that at point alpha, right, stress X is not equal to stress max, and the shear stress is also not equal to the shear max at all at point alpha. Then some of you will say, Eugene, then why are we considering that point? Okay, why are we considering this point? Because at point alpha, okay, point alpha, okay, we have the radius over here. Okay, so at point alpha, the radius r are inducing or are causing stress concentration. Okay, they are causing stress concentration. So if this structure were to break in the cross-sectional view, it will break at point where? Alpha. Okay, because we have a sudden change in what? There are two things why it will break. You have a sudden change of what? You have a sudden change in thickness. So from T over here, T1 over here, you have T2 over here, and T2 is so much smaller. And you have the radius over here. The radius is going it's going to induce stress concentration. So for this course, I will not tell you, or we will not determine how this radius will magnify the stress. That will be taught in the next course that you take after this, which is 303. Okay, this course I'll teach you how to analyze the stresses only. Okay, right. So we know we are going to determine at point alpha now. Okay, we are going to see things, or we'll determine the stresses at point alpha. Now let me copy this image again. Okay. So we are now going to look at point alpha. Okay, and I'm also going to take this one. Okay, so we are going to take this point. We are going to position an element at point alpha. Okay, so we're going to put an element down here. So this is our element alpha. Okay, so element alpha, you ask me where is it placed? Is placed down here. Okay, that is our element alpha. So now I'm going to blow up the view of element alpha. Okay. So this is X, this is Y, and this is Z. Okay, remember, we are in a 3D world. Our design is also in a 3D. Okay, so I'm going to draw the element. So we're going to draw element alpha. So this is our element alpha. Okay, so if we were to look at point alpha, right? So it does not matter whether you take the top or bottom for this case, okay, because it's symmetry. So for this case, you can assume, right? You can assume that this is your stress X, okay, and we can also assume that this is your shear XY, and the other arrow is your shear YX. Okay. So now we have to determine our stress X and our shear XY and shear YX. Do not worry for now, like how you know the direction. Okay, as I said, this is an introduction. I'm just showing you how to assemble everything together at the end of this course. Okay, which you have to know, because as I said, this is a exam question. Okay, so now we have to determine stress X. Okay, so we know that stress X is equal to mz over izz multiplied by y. So the y distance is up to element alpha at element. So we have to know. So for this case, we already know mz, right? Mz is